distributivity and the existence of existentiality and inverse. And yes. So first we have the global commutativity. We have the associativity. Inverse. Then we have identity. Now, for all these properties, distributivity. Okay, distributive. Yes. Existence of identical elements.
You also have additive.
If it is additive, it will not be for addition, right?
Yes.
The multiplication. So all these are for additive and multiplicative elements. Now, this we say that we're talking about complex number. So what we're using is say let z to be equal to x plus I1. Right? So this is a complex number z. Now what we're saying now is this: if we have for the closure property, whatever addition is added to this complex number, let's say maybe a scalar or another complex number. Let's say this is C1, X1, Y1, and this is D2. First of all, X2 plus what? Y2. So what this means now is that if we have Z1 to the Z2, which is also an element of the complex number, then we will not say that the complex number is closed. You understand? Now, the proof for this is this. Proof. What is happening here is this. So if we add Z1 plus Z2, which is equal to X1 plus IY1 plus X2 plus what? IY2. So what we have here is we open the bracket by saying X1 plus IY1 plus X2 plus what? IY2. So what we have here is, so we now have the real part and we also have the imaginary part. So we have that X1 plus what? Y1.
No, X2.
Sorry, X2. So X1 plus what? X2 plus what? Y1 plus what? Y2. So this is the real part and this is the imaginary part, which is clearly that this is an element of what? Complex number. Now, so it means this is closed under what? Addition. Now, for the multiplication, we say that Z1 is equal to X1 plus IY1. Z2 is equal to X2 plus what? IY2. Now, we say that Z1 times Z2 is equal to X1 plus IY1. X2 plus what? IY2. So are you getting this down? Okay, good. Now, when we open the bracket by expansion, so we have X1, open bracket, X2 plus what? IY2 plus IY1, open bracket, X2 plus what? IY2. So by expansion, we have X1, X2, X1, X2 plus X1, Y2 plus X2, Y1, then plus I times I squared, Y1, Y2. So this is equal to X1, X2 plus one I here and I here, right? So it's come out. So I open bracket x1 y2 plus what? x2 y1. Then this is minus. That is I square is equals to what? Minus 1. So we have minus y1 y2. So this is real, this is real. So you collect this and this. So we have that x1 x2 minus y1 y2 plus I open brackets x1 y2 plus what? x2 y1. And so this is the real part and this is the imaginary part. So which is clearly an element of the what? Complex number. So it means the complex number is closed under addition and the what? Multiplication. So do you have this down here? Yeah. Okay, cool. Now we test for commutativity. Now for addition, we say that let z1 to be equal to x1 plus iy1 and z2 to be equal to x2 plus what? iy2. Now, commutativity says that z1 plus what? z2 is equal to what? z2 plus what? z1. Now, for the left hand side, we have that z1 plus z2 is equal to x1 plus iy1 plus x2 plus what? iy2. So we have here that this is equal to x1 plus what? x2, right? Plus I open bracket y1 plus what? y2. This is what we have, right? Now z2 plus z1 is the same thing as x2 plus what? iy2 plus x1 plus what? iy1. So what we have here is x2 plus x1 plus I open bracket y2 plus what? y1. Right? So this is the real part, this is the imaginary part. Now, but remember, in the properties of real number, they are commutative, right? So it means x1 plus x2 is the same thing as x2 plus what? x1. So which implies that z1 plus z2 is equal to what? z2 plus what? z1. So the commutativity now is ascertained for addition. Now for multiplication, we have that z1 is equal to x1 plus iy1, z2 is equal to x2 plus what? iy2. Now, what we're having here is z1, we need to show that z1, z2 is equal to what? z2, z1. Now, for the left hand side, z1, z2 is equal to x1 plus iy1 times x2 plus what? iy2. Now, expanding, we have that x1 open bracket x2 plus iy2 plus iy1 open bracket x2 plus what? iy2. Expand multiplying, we have that x1 times x2 plus I x1 y2 plus I x2 y1 then plus I squared y1 y2. So here we have that x1 x2 I is common. So plus I open bracket x1 y2 plus what? x2 y1. Then I squared is equal to what? Minus 1. So we have minus y1 y2. So here we have, this is the real part, this is the real part, and this is the imaginary part, so we collect. Now we have x1 x2 minus y1 y2 plus I open bracket x1 y2 plus x2 y1. So this is the value for z1 z2. So now we find the value for z2 z1. For z2 z1 we have z2 z1 equal to x2 plus iy2 times x1 plus iy1. Now, skipping these steps, then our final answer will be what?
x1 y2
x2 x1, right?
yes x1 yes
Minus y2 y1.
yes I okay.
I'm giving the final answer.
Okay, yeah.
I'm not expanding this time, so I'm giving the final answer. So, what do we have? x2, x1. You can get it from this place.
Yes.
x2, x1 minus what? y2, y1 plus I, right there.
x1 y2
y2, x1 plus what?
y1 x2
y1, x2. You understand?
yes.
Now, if you look at this, you see that x2, x1, this is x1, x2. And multiplication of real number is commutative.
Yes.
That is 2 times 3 is 7 times 3 times 2.
Yes.
So, therefore, this is commutative. This is also commutative alongside with this. So, therefore, z2, z1, z2 is equal to what? z2, z1. So, addition and multiplication is commutative under complex number. Now, so we talk about associativity. We said that let z1 to be equal to x1 plus iy1. z2 to be equal to x2 plus iy2. And z3 to be equal to what? x3 plus y3. Now here it suffices to show that for under addition, the associativity is z1 plus z2 plus what? z3 is the same thing as what? z1 plus z2 plus what? z3. So this is the statement for associativity. Now the next one is to prove that this is equal to this. So here we will have that for the left hand side, z1 plus z2 plus z3 is equal to x1 plus what? iy1 plus x2 plus iy2 plus x3 plus what? iy3. So this is what you have here. Yes. Now we need to open the bracket. So we have x1 plus iy1 plus, so here is x2 plus iy2 plus what? x3 plus what? iy3. So here is equal to x1 plus iy1 plus x2 plus x3. Is that clear?
Yeah.
Plus y2 plus what? y3. So this is what we have. So we can now add the real part and the imaginary part now. So we have that x1 plus x2 plus what? x3 plus I open bracket y1 plus y2 plus y3. So this is the left hand side. So we need to show for this part now. By something we have that z1 plus what? z2 plus what? z3. So we have this x2 x1 plus what? iy1 plus x2 plus what? iy2. Then plus x3 plus iy3. So here we have that we perform the operation in the bracket. So we have x1 plus what? x2 plus y1 plus what? y2. Then plus the last part, which is x3 plus what? iy3. So here you cannot add the real part and the imaginary part. So we have x1 plus what? x2 plus x3 plus y1 plus what? y2 plus what? y2. So clearly now it can be seen that this is equal to what? This. So therefore z1 plus z2 plus z3 is equal to what? z1 plus z2 plus z3. So this is for associativity under addition. Okay? Now we need to check for the multiplication. Now for the multiplication we have that z1, z2, z3, z1 times z2, z3 is the same thing as z1, z2 times what? z3. So performing on the left hand side, we have that z1 open bracket z2, z3 is the same thing as x1 plus x plus iy1 x2 plus iy2 x3 plus what? iy3. Now for us to do this expansion as fast as possible, we need to jump some procedures. So what we're going to do is this is x1 plus what? iy1. Let's do this. So this is x2, x3, right? x2, x3 plus I open bracket
y2,
x2, y3, x2, y3 plus
Sir, y2, y3.
So which will be I, x2, y3? I should be to be
So no, this is what is happening.
I understand.
This times everything here, so I have x2, x3
Yeah.
plus I is common. So this x2 times y3,
Where is it?
right?
Yes.
Then plus this times this.
Yeah.
But remember, the I is out already.
Yes.
So we now have plus x3, y2, right? Now we need to multiply the last part,
I square.
which is minus
Minus what? Y2.
minus y2.
y2, y3, right? So here we have x1 plus iy1, x2, x3 minus y2, y3 plus I, x2, y3 plus x3, y2, right? So what we need to do now is to expand now
Yes.
as equal as it is. So we have this is equal to
X1.
x1 times everything here,
Yes.
right? So we have x1, x2,
X3.
x3
Minus. Minus. X1.
minus x1,
Y2.
y2,
Y2.
y3, right?
Plus.
Plus
I.
I,
Outside. X1.
x1,
X2.
x2,
Y3.
y3 plus
X1.
x1, x3,
Y3.
y2, right? Then this plus I, open brackets,
X2.
x2, x3,
Y1.
y1
Good. Minus.
minus
Y1.
y1,
Y2.
y2, y3. I is what? I squared.
Y3.
That is minus 1. Then open brackets, this now.
Y1.
That is x2, y1, y3 plus
X3. Y1.
x3, y1, y2. You can still expand so that we can do away with the brackets, right? So the first part is what? x1, x2, x3. We still have three parts here. Minus x1, let's open bracket all through and see what we can collect. Minus x1, y2, y3. This right? Minus x2, y1, y3.
Minus again, x3.
Minus x3,
Y1,
y1,
Y2.
y2. So we're done with this and this, right? Then plus I, open bracket, x1, x2, y3 plus x1, x3, y2.
Plus I.
The I is here now.
Okay.
Then x2,
X3, Y1.
x3, y1,
Minus.
then minus
Y1, Y2,
y1, y2, y3. So when we're done with this, and we're done with this. So this is that's the value for z1, z2, z3. So we also need to test for, please write this. We also need to test for z1, z2 times what? z3. Alright, do that. Let's see what we have. is known as complex number under associativity. Now, so we talked about the existence of identity. The existence of identity. So first we talk about the additive identity. So we said that if z is equal to x plus iy, then there exists 0, which is the same thing as 0 plus I0. That makes it a complex number, an element of a complex number, such that z plus 0 is equal to 0 plus z, which is equal to what? C. So this is the existence of additive identity, and this is clear. We prove is that z is equal to x plus iy. Then z plus 0 is the same thing as x plus iy plus 0 plus 0i. So we have z plus 0 to be equal to x plus 0 plus iy plus what? 0i, which is the same as x plus iy. Now also we have that 0 plus z is the same thing as 0 plus 0i plus x plus what? iy, which is the same thing as 0 plus x plus 0i plus what? iy. So we have x plus what? iy. So which implies that z plus what? 0 is equal to what? 0 plus z, which is what? Equals to z. Which is equal to x plus iy. So there is existence of identity of the x. Now, for the multiplicative identity, we have that if z is equal to x plus iy, then there exists 0 plus I there exists 1 plus 0i, which is an element of a complex number such that z1, which is z times 1, is equals to what? 1 times z, which is equals to what? Is that? Yes, that is for the multiplication. Yes. We're still the same thing now, we're still giving the same answer. So, since whenever you multiply 1 with z and you do not change the value, so that makes it what? Multiplication identity. So, the proof is that c1 is equal to x plus what? I1 times 1 plus what? 0i. So which is the same thing as x open bracket 1 plus 0i plus iy open bracket 1 plus what? 0i. So this is the same thing as x plus 0 plus what? Iy plus what? 0. So therefore this is the same thing as x plus what? Iy. And which is equal to what? 0. Similarly, we can say that 1 times z, which is equal to 1 plus 0i times x plus iy. By expansion, we have that 1 open bracket x plus iy plus 0i open bracket x plus what? Iy. So by expansion, we have x plus iy plus 0 plus 0. So which is the same thing as x plus what? And iy, which is equal to what? Z. So therefore, z1 is equal to what? And z, which is equal to what? Z. So this is a proof for the self-identity for addition and multiplication. Now we'll go for what? Inverse. Inverse. Of inverse element also. Now we say that if which is x plus iy, the complex number, then there exists minus z, which is equal to minus x minus iy. Is that clear? Yes. Which is an element of a complex number. See, then z plus minus z is equal to minus z plus what? Z, which is equal to what? 0. Whenever the additive inverse now will have to give you the additive identity for the final answer there. So you know 0 is the additive identity. So the proof goes, we have that z plus minus z is equal to, this is what? X plus what? Iy, right? Plus minus x minus iy. Yes. So we have that x by open bracket plus what? Iy minus what? X minus iy. So collecting like terms, so you have x minus x plus iy minus what? Then the final answer is what? 0. 0.
Similarly,
so we have that z plus minus z plus z is equal to minus x minus iy plus x plus iy. So by opening the bracket, we have minus x minus I plus x plus iy. So collecting the like term, so we have minus x plus x minus iy plus iy. So this is equal to what? 0. So we have therefore z plus minus z is the same thing as minus z plus z, which is what? 0. So this is the instance of additive inverse. So what happens for multiplicative inverse? So we say that if z, which is x plus iy, is a complex number, then there exists z inverse, which is an element of a complex number, such that z inverse is equal to z inverse z, which is equal to what? 1. So this is the statement for the multiplicative inverse. So if we have z to be equal to x plus iy, which implies that z inverse is equal to what? X plus iy raised to the power of what? Minus 1, which is the same thing as what? 1 over what? X plus what? Iy. But remember, the law of indices that you know is also applicable when we're talking about complex numbers.
Yes.
But in the other way around, we can say that z inverse is the same thing as x plus iy, x plus iy minus 1. Right? Now, this power is what? 1. So we have x plus iy, 1
Minus 1.
1 plus minus 1.
Yes.
Right?
Yes.
So which is x plus iy raised to the power of what?
0.
0, which is equal to what?
1.
1. So any number is equal to 0 is what?
1.
Okay, thank you very much. The subject, okay, thank you. Thank you so much. Right. X plus iy raised to the power of 0 is 1. So any number is to the power of 0, both complex and the rest is equal to 1. Now, this is one of the simplest procedures for finding, to prove this. Yes, the multiplicative inverse. Now, the other way around, z inverse z will still give us what? 1. So we say therefore, we don't say therefore, z inverse is equal to what? Z inverse z is equal to what? 1. Now, that is x.
Distributive.
we have two laws for the distribution. So the one addition over multiplication and multiplication over what? Addition. So distribution. So we're saying if z1 is equal to what? x1 plus iy1, z2 is equal to what? x2 plus iy2, and z3 is equal to what? x3 plus what? iy3. Then one z1 open bracket z2 plus z3. So what do we have? z1 z2 plus what?
Z3.
z1 z3.
Okay, yeah.
So this z1 is distribution over z2 plus z3. Then the second one is what? We have z1 plus what? z2 times what? z3, which is equal to what? z1
Z3
is plus
Z2 Z3
plus z2
Z3.
z3. Right.
Okay.
So these are the statements for the distributive law of complex numbers. And this is clear to prove, right?
Yes.
This is very easy to prove. So we'll leave this group as an exercise, okay? Right there. So we will do an exercise for you to verify that this is equal to this and